Welcome to Math TV with Professor V. In this video, we're going to go over how to find critical values or critical numbers, same thing. The purpose of this video is just to help you with the mechanics and the computational aspect of computing critical values. If you need more of the background information as to what they are, their meaning, how to interpret them, then I'll link the video here from my Calculus 1 video lectures playlist. That is more a classroom style lecture that gives you all of that background. Okay, but just to recap, when we're finding critical values or critical numbers, they come from one of two places. First, you compute your derivative, f prime, let's say, and then they either come from where f prime of x is equal to 0 or where f prime of x does not exist. All right, burn that in your brain. The other thing to remember is that critical values must be in the domain of f of x. So that's why whenever I start a problem, I'm going to list out what the domain is for the function. That way when we're solving for critical values, we don't accidentally report a value that is not within the domain of the function. All right, good. So let's just look at a few examples here that are pretty standard for what you might run into. So say the directions are find the critical values or find the critical numbers for the following functions. And the first one that we're going to look at is f of x equals x to the 4/5 times x minus 4 squared. All right? So first order of business, we have to figure out what the domain is for f of x. So let's analyze this function a little bit. So I notice this term here is x to the 4/5. Remember, that is the same as the 5th root of x to the 4th. Now, when you have a radical function, if the index is odd, there are no restrictions because remember, we can take an odd root of a negative number. So no reason to restrict the domain from that term. And then I look at the other term here and it's the quantity x minus 4 squared. That's basically a polynomial quantity. So we don't have any restrictions there. That means the domain for f of x is all real numbers or negative infinity to infinity. Good, that's out of the way. Now it's derivative time. So when we take the derivative, I already notice that there's two smaller functions that make up f of x that are being multiplied together. So I need to use the product rule. Here we go. All I do when I take the product rule is I think the two functions take turns having their derivative taken. So first, let's take the derivative of x to the 4/5. I'm going to bring the exponent down in the front and then subtract 1. That's my new exponent. So 4/5 minus 1 is negative 1/5. And then you leave the other term, the other function alone. So leave alone x minus 4 squared. Plus, and then now they take turns. So then leave x to the 4/5 alone. And then now I'm going to take the derivative of x minus 4 squared. So in that case, I'm going to use the chain rule. You bring the 2 down in the front, subtract 1 from the exponent, leave that x minus 4 alone, and then by the chain rule, I have to multiply by the derivative of x minus 4, but that's just 1. You don't have to write that times 1 at the end, but I just did it so you guys know I'm thinking about it, and sometimes it's not 1. Okay, most of you guys are pretty good about getting up to here. It's the next few steps that a lot of students struggle with. So as soon as you notice there's negative exponents, you got to put those in the denominator, rewrite them as positive exponents. So look what we're going to do with this first term. I've got this x to the negative 1/5. I'm going to put that in the denominator with the 5, and then leave 4 times x minus 4 quantity squared in the numerator. Okay. Plus, and then let's look at the second term. Well, there's no negative exponents, but I'm just going to rewrite it so it looks a little cleaner. So I'll put 2x to the 4/5 first, and then I have x minus 4, and I'll just put this over 1 because maybe you can anticipate what I'm going to do next. Remember, when you're finding critical values, you want to know where the derivative equals 0, which basically is the same as setting the numerator equal to 0. And then you also want to know where the derivative does not exist, which comes from setting the denominator equal to 0. So you want the f prime of x, or the expression for f prime of x, to be one term whenever possible. Okay, so I'm going to add these guys together. I need to get a common denominator. Can you see what the common denominator is going to be? Yes, it's 5x to the 1/5. Okay, so let's multiply this second term here by 5x to the 1/5 and then see what happens. So we have 4 times the quantity x minus 4 squared plus, now look. So 2 times 5, those are my constants, that's 10. And then, oh, this is so cool. So we have x to the 4/5 times x to the 1/5. So I add those exponents together, right? 4/5 plus 1/5, that's just 5/5, so that's 1. So I've got x to the first. Oh, how nice. And then you still have that x minus 4. And this is all over 5x to the 1/5. Beautiful. Now you want to get yourself set up so that you can really solve and find those critical values easily. So let's see if we can factor that numerator more. Don't multiply it out. No. Because look, I've got an x minus 4 squared in the first term and then x minus 4 to the first in the second term. So I can factor that out. And also I can take a 2 out from both of those terms. So you always want to take out the GCF. So let's take out a 2 and an x minus 4. Okay, so now what's left over? So I took a 2 and an x minus 4 out, so I still have 2 and only one x minus 4 in the first term. Plus, and then let's look at that second term. I took a 2 out, so now all I have is 5x, and that x minus 4 is gone. Over 5x to the 1/5. All right, so nice. Now let's just clean up inside those brackets. So this is 2x minus 8, and then I have plus 5x. So we're going to be left with 2 times x minus 4 times 7x minus 8 over 5x to the 1/5. Okay, there's our derivative all cleaned up and pretty, ready for action. So now that we have f prime of x all nicely factored and written as one term, it's critical value time. And always list them out this way. Step 1, you find them where f prime of x equals 0, which would mean you set the numerator equal to 0. So if I set the numerator equal to 0, since it's so nicely factored, I can tell that means either x is equal to 4 or x is equal to 8 over 7. And the second place where we get critical values is where f prime of x does not exist. That would mean the denominator equals 0. So that would mean 5x to the 1/5 equals 0, which only happens if x is equal to 0. So here we have our 3 critical values, 4, 8/7, and 0, and they're all fine to include in our final answer because remember, the domain for f of x was all real numbers. Okay. Good. Let's look at another example, maybe something a little more spicy. Example 2. This time our function is equal to the natural log of x over x to the 4th. All right, so let us start off by looking at what the domain of this function is going to be, remember? Okay, natural log of x. I know domain for logarithmic functions is restricted. The argument has to be positive. The argument is this stuff here. It can't even equal 0. Remember the graph of natural log of x? Hopefully you're imagining it right now. We've got that vertical asymptote at the y-axis. Oh yeah, oh yeah. All right, so that means x has to be strictly greater than 0. What else? Look at the denominator. I've got x to the 4th. That means x cannot equal 0. Otherwise, the expression would be undefined. But you know, that restriction's already taken care of. If I say x is greater than 0, then obviously x can't equal 0. So the domain, I can just write out in interval notation as the interval from 0 to infinity, not including 0. Okay, good, that's done with. Now it's derivative time. So here we go. This time I need to use the quotient rule, right, to take the derivative. So we've got, I like to sing the song here, Lodi high, so x to the 4th times derivative of natural log of x is 1 over x, minus high d low, so numerator times derivative of the denominator over low. So x to the 4th squared is going to be x to the 8th. Good, now let's clean up. So we've got in the numerator x cubed minus, you know, I'm going to rearrange that second term and put the 4x cubed in the front just so it doesn't get confused with what the argument is on natural log, right? The argument is just the x. So it's safer. Put that 4x cubed in the front over x to the 8th. And then, you know, we can simplify this because I can factor out an x cubed. And then I have 1 minus 4 natural log of x over x to the 8th. And voila, the x cubed cancels. This is now a 5. So we have 1 minus 4 times the natural log of x over x to the 5th. That one was easier than the last problem, huh? To get it nice and cleaned up, don't you think? Okay, it's critical value time. So remember, critical values come from two places. One, where f prime of x equals 0. So we're going to set the numerator equal to 0. That's how that would happen. That would mean the natural log of x equals 1/4. So x equals e to the 1/4. All right, is that within my domain? Remember, the domain was from 0 to infinity. E to the 1/4 is not negative, so that's fine. And then the second place where we get critical values from is where f prime of x does not exist. So that would mean the denominator equals 0, which would mean x is equal to 0. But remember, that's not included in my domain. So you could write that is not an element of the domain. So it's not going to be a critical value. No, don't report it. So sorry. Okay. So for your final answer, your critical value, you only have one. It's x equals e to the 1/4. All right. Good. So that's why it's super important to list out what the domain for your function is at the very beginning of the problem. That way, when you run into potential critical values that are not in the domain, you don't forget to throw them out. Good. And if you think about it, it should make sense. It can't be a critical value. It can't be a critical point if it's not even part of your graph. It's not in the domain. Let's look at one more example that I'm going to do for you. And this time we're going to look at a rational function, f of x equals 16x over x squared plus 16. Okay, so for a rational function, you just want to make sure the denominator doesn't equal 0. But if you notice, x squared plus 16, that's never going to equal 0. It only has imaginary solutions. So actually, we have no restrictions here. The domain's all real numbers. Okay, it's derivative time. So f prime of x is going to equal, looks like we got to use the quotient rule again. So we've got low, leave the denominator alone, d high, take the derivative of the numerator, minus high, d low, derivative of x squared plus 16 is 2x over low. So over x squared plus 16 squared. Okay, good. Now let's see here. I mean, you have a couple options. You could multiply everything out in the numerator, but I tend to try to factor first because it makes life a lot easier. See how I can take a 16 out of both these terms? Well, then do it, okay? I'm going to take out a 16, and then I just have x squared plus 16 minus, look what's left over in that second term, just a 2x squared. My goodness. Over x squared plus 16 squared. Okay, and then I can just clean up inside those brackets. So I have 16 times, notice we have x squared and then a negative 2x squared. So that's negative x squared. I'll write this as 16 minus x squared over x squared plus 16 all squared. So there's my derivative. And notice, since I always try to factor, it's really nice and easy to find where f prime is 0 and where f prime does not exist. All right, here we go. Critical value time. So first, where f prime of x equals 0, that implies the numerator is 0. I don't need to pay attention to this 16. That's just a constant. It's not going to give me any critical values. But 16 minus x squared equaling 0 will. That means x squared equals 16, so x would equal plus or minus 4. Those are critical values. Those are within the domain. Remember, the domain's all real numbers, so we are good. And then second place where we get critical values is where f prime of x does not exist. So that would come from the denominator equaling 0. But remember, in the very beginning, when we were finding the domain of our function, we realized this x squared plus 16, that expression does not have any real zeros. They're imaginary. So the only critical values that we have are plus or minus 4. Okay, that's it. I have one more if you guys want to try it on your own. Okay, and then I'll walk you through the solution. So what I recommend, if we were in class, I'd put this one up, have you do it, and then we'd go over our answers together. Okay, so f of x is equal to x to the 1/3 times x squared minus 63. Now please, you'll only benefit from this if you take the time to pause the video, try it on your own, and then watch the solution. Okay, to get better at math, a lot of the time it just boils down to practicing. So pause it here and then try it on your own. We'll go over it in just a second. Okay, did you list the domain first? I hope so. So x to the 1/3, that's the same as cube root of x. So there's no restrictions because this index is odd. And x squared minus 63 doesn't have any restrictions, so the domain's going to be all real numbers or negative infinity to infinity. All right? Good. Again, we have to use the product rule. Did you notice this is similar to the first example that I did? So f prime of x is equal to, I'll take the derivative of x to the 1/3. 1/3 x to the negative 2/3. Leave this alone. Plus x to the 1/3. Now I take the derivative of x squared minus 63, which is just 2x. Okay, and then again, I see I have a negative exponent, so that's going to go in the denominator. So we have x squared minus 63 over 3x to the 2/3 plus, and then I can add these exponents. This is x to the 1/3 and this is x to the 1st. So we have got 2x to the 4/3 over 1. I'm going to put it over 1 because I know it's common denominator time. So I'm going to multiply by 3x to the 2/3. So here I have x squared minus 63 plus 2 times 3, that's 6. X raised to the, now pay attention, I add these exponents. 4/3 plus 2/3, that's 6/3, which is 2, over 3x to the 2/3. Ooh, did we get it right up to here? Give yourself a pat on the back if you did. All right, and then I can combine like terms in the numerator. So we've got 7x squared minus 63 over 3x to the 2/3, and then I can factor out that 7. Then we have x squared minus 9. Oh my goodness, this is going to work out beautifully. Over 3x to the 2/3. There's our derivative, all spruced up, ready for action. All right, so critical values come from two places. One, where f prime of x equals 0. That would mean the numerator equals 0. So x squared minus 9 is 0. The 7's doing nothing for us. So x equals plus or minus 3. Second place is where f prime of x does not exist, which would mean the denominator is 0. 3x to the 2/3 is 0. That only happens if x is 0. And remember, our domain was all real numbers, so everything gets included just fine. So our critical values are plus or minus 3 and 0. Okay? Good. Now, just as far as terminology, some books call these critical numbers, critical values. If you see that you're being asked for critical points, just make sure you give the y value as well. So it would want x comma f of x. You take your critical value and then you plug it back into the function. So if it's a point, then it wants an ordered pair, a point to plot. If you're just asked for a critical number or critical value, then you only need to report the x value. Okay? I'll link my other video here if you want to see more about once you find the critical values, how you test for local extrema and all of that. But this was just to help you with the mechanics. Hope you enjoyed it and found it helpful. Don't forget to give it a thumbs up and subscribe if you haven't already. And stick around, we've got more quick tips coming your way.